Hi, welcome. In this video, we will solve problem remove the nth node from the linked list asked by companies like Amazon, Facebook, Microsoft, and Google. Now let's check out one more problem on linked list. So remove the nth node from the end of the list. So we have given the head of the linked list. We need to remove the nth node from the end of the list and we need to return the head. So if we can check this example, we have 1, 2, 3, 4, 5 as an list, linked list. We need to remove the second node from the last. So this is the second node from the last. If I remove 4, it will be something like 1, 2, 3, 5. Similarly, we have 1 in a linked list. If I removed 1, there will be a null in my list. Okay. So now let's see. So here we have nodes and let's create a linked list. So we have 1, 2, 3, 4 and 5, where 1 is representing to 2, 2 has an address of 3, 3 has an address of 4, 4 has an address of 5 and 5 has an address of null. 5 is basically pointing to null. And I want to remove the second last node here. So this is my second last node. And if I want to remove this, we put with red pen. If I want to remove this one, basically what I need to do if I want to remove this one, I will break this connection. Okay, I don't want that my node 3 store the address of 4, it should store the address of 5, right? So I want to change the address of the previous node, like the one, the last that I'm deleting, right? So this is the point, this is the node that I'm deleting. My main point of concern is this node, right? Because I want to change the address of this node. My final linked list will be look like this, where 1 has an address of 2, 2 has an address of 3 and 3 has an address of 5, not 4. 5 is pointing to 10. So my important node that I need to work on is this node, right? Not this one that I'm deleting it. So yes, like any approaches, any thoughts how you can solve it? So now let's discuss the approach one, the very brute force one that is coming to my mind, that I want to delete this second node, right? So I need to traverse till here basically, and what I will do, I will simply change the address. So suppose this is pointing to current, suppose somehow I travel to this point, and I will simply say current dot next equals to current dot next dot next. Simple, right? This is the thing that I only need to do once I reach to this point. So how I will reach to this point? So basically what I will do, I will take one count. Okay, I will take one variable count and I will count all my nodes. What are the total available nodes in the linked list? So here, what are the total available nodes? That is 5. Okay, so my count will be 5. And what is the node number that I need to delete? I need to delete 2 from the last. So if I do count minus n, that is 5 minus 2, can I get the position from the starting? This will be my position from the starting, right? That I will need to step here at the position 3, and then what I will do, I will simply change the address. Okay, now the only thing is, suppose you got n equals to not 2, 5, and your count is also 5. So 5 minus 5, you will get 0. So position is now 0. So basically you can do a check. If your position is 0, right, that means position 0 means that n is equals to 5. N is equals to 5 means that you are deleting the first node. If you are deleting the first node, then what you will return? You will return this. So basically that what you need to do, you just need to do head dot next, and whatever the pointer is, suppose like your head is pointing to this, so head dot next will be your answer. Yes, so this will be one approach that we can apply. So basically what I'm saying, let's try to write a pseudo code of it. So basically
I will use one current pointer that is pointing to head of the linked list. Okay, I will start with one count that is starting from 0, and I will simply count what are the total nodes. So while current not equals to null, I will count the total nodes. Current equals to current dot next. Basically, I am traversing and I am counting all the nodes. Count plus plus. So this will give me the nodes. I will get the nodes. Once I get the nodes, what I will do, I will find the position from the starting. And how I will find the position from the starting? I will basically do count minus n. Right. If I get count minus n, okay, then I will check. Basic one check will be if suppose position is equals to 0, okay, that means I am deleting the first node. I will simply say return head dot next, okay, and the next thing is suppose if position is not equals to 0, so then what we will do, we will simply start a loop and we will reach to that index. So basically I will start with current again equals to head, and here now count will be start from 1. I am starting from 1 because third will be my this node, right? This is the first node, second node and third node, and third node I need to stop it, so I will start from 1, right? So I will start from 1. I will check while current not equals to null, I will simply run like your current equals to current dot next, and you will update the count plus plus. But suppose somehow if your count is equals to your position, what I will do, I will simply say this is the main logic, right? So what I will do, I will simply say it is current dot next equals to current dot next dot next. It will be, let me write it here. Current dot next equals to current dot next. Okay, and then I will break it. Simple, right? And in the last I need to return head. So this will be my approach 1, right? This is how I can solve it. And what will the time complexity of it? So basically here you are calculating all the nodes. So current is starting from head to like to the end of the linked list. So this will run for n times. Okay, then here also we are running till position. Okay. Depends, suppose in the worst case the position may be the last one, so this will also run nearly n times, this is also run n times, so the time complexity will be somehow 2n, and the order of n I will say, so the time complexity will be order of n only. We are not taking any space, so space complexity will be constant. Okay, so this will be time complexity and space complexity of this approach. Now one more approach that we can try, basically again let's check out our problem. What is the problem? 1 pointing to 2, pointing to 3, 4 is pointing to 5, and 5 is pointing to null, and I want to delete this second last. Okay, so basically again a focus node will be this one. So what I will do, I will take 2 pointers, again one fast and slow. Okay, and n is 2, so I will run my pointer, the fast one, 2 times. So fast will move to here and then it will move to here, basically 2 times. So one traversal, then second traversal. Okay, and then I will take one slow pointer. And why I am taking a slow pointer? Because I want a difference of 2. I want a difference of 2 because n is equals to 2. I want a difference of 2 so that when my fast is reaching to the end, my slow will be here. See, now what I will do, I will move both the pointers side by side. Fast will move here, slow will move here. Again, fast will move here and slow will move here. And now you can see when my fast is at the end, last of the linked list, my slow pointer is on the main, like the main node that I want. Then what I will do, I will simply connect it like this. Again, there will be some edge cases, but yeah, that this is one possible. You can understand this by many examples. Let me create more nodes so that I can show you. Let's create a big linked list. Yeah. So that we'll get this example more clearly. So 1 has an address of 2, 2 has an address of 3, 3 has an address of 4, 4 has an address of 5, 5 has an address of 6, then 7, then 8, and 8 has an address of 9. 9 is pointing to null. And suppose you are deleting the fourth node. Okay, so first, second, third, fourth, this node I want to delete. Okay, so again my focus node will be this one. So what I will do, I will take one fast pointer and I will run for 4 times. So 1, 2, okay, 3, and then 4. This is not 5 times, this is 4 times. Okay, so basically it is started from here now. It is started from here. So 1 time, 2 time, 3 time, 4 time. And now my slow pointer will be here, so such that the difference between fast and slow will be of 5. Sorry, 4. You can see 1, 2, 3, 4. 4 difference. Right? Why I want basically this 4 difference? Because from the last it has a fourth node that I want to delete. So if my fast pointer will be here, if my fast pointer will be here, my slow pointer will be somehow here, maintaining the difference of 4. Okay, so now let's see. My fast pointer will move by 1, my slow pointer will move by 1. Okay, again my fast pointer will move by 1, my slow pointer will move by 1. Again my fast pointer will move by 1, my slow pointer will move by 1. Again my fast pointer will move by 1 and slow pointer will move by 1. And when I reach to the last node, that fast dot next is null. When I am reaching to the last node, I will stop it because that is my main node. And what I will do once I reached here, I will again break the connection. Slow dot next equals to slow dot next dot next. Okay, and yeah, this will be the thing only. Again, there will be some edge cases, right? Like suppose here n instead of 2, n is equals to suppose 5 only. So when if n is equals to 5, that means you want to delete this node. But how I will get to know? Because I'm simply moving my fast pointer. So if I am moving my fast pointer till n equals to 5, that means my fast pointer will be somehow at null. And if my fast pointer is at null, that means they are saying that I need to delete the first node from the start. So I will simply return head of the linked list. We can separately check the edge cases for it. Okay. So in the next video, we will do the code of it, right? How you can implement it. But this will be the approach. Let me write the pseudo code of it so that we will get a bit clarity of time complexity and space complexity. So what I will do, I will simply take one count variable, or I guess here, yeah, for this one we will use one count variable. Okay, so count is starting from 0. Okay, and we have one fast pointer that is pointing to head. We have one slow pointer that is also pointing to head, and I will run while count is less than n. what I will write inside this code, that fast will be fast dot next, basically it will traverse, and my count will be count plus plus. Okay, once it will done, I have a gap of fast and slow, right? Then I like slow is equals to head, but fast has a gap of count, that is gap of n basically. Now how I will understand the edge cases, basically if n is equals to 5, that means I can say my fast pointer is pointing to null. If it is pointing to null, I can directly say return head dot next. But if this is not the case, what I will do, I will simply run a loop again while fast dot next not null. Remember, not fast. Fast next not equals to null. I will run it both the pointers. That means I will run slow equals to slow dot next, fast equals to fast dot next. Okay, and once I will come out from this loop, okay, I will write the main condition, that is slow dot next equals to slow dot next dot next. Okay, and in the last we will return, and that's it. That's the code of it. So here how many times it is running? Okay, so it is running till n times, I will say this n. Okay, so we will confuse with this n. Let's take capital N for the number of nodes. All right, so here I am running, this loop will run times, right? And this from here fast will run to ends. So you can see like your fast started from here with the 4, and then it is completed the distance. So by both the loops, right, this one and this one, by contributing of both the loops, you will run only n times, that is n times, capital N times, right? So that's why the time complexity here is linearly depending completely on n, right? Not 2n or 1.5n. It is completely on n. So time complexity will be big of n, and again space complexity will be constant, right? And this is a much fastest approach, right? Suppose there are 1000 nodes, so your answer will be come in 1000 iterations only. Okay, most probably it will not go for 2000. Okay, so this will be the time complexity and space complexity of this approach. And in the next video we will check out the code implementation of both the approaches, and then we will check out the dry run of this code.